Welcome to the webinar about unit testing and code coverage measurement with the unit testing tool Tessy. First of all, I would like to give you a quick overview of the company Hitex. We were founded in 1976, so we are more than 40 years old. Hitex is a 100% daughter company of the Infineon Group since 2003. We provide development and software quality tools, and that's the reason why I'm speaking here today to you, because Hitex is responsible for sales, marketing, training, first level support for the unit testing tool Tessy, and Hitex also provides test services using Tessy. This means you can pass your source code to Hitex and we test it and you get it back well tested. We do a lot of different other things like engineering, production, consulting, and last not least, we are Aurix preferred design house. And now some organizational things. During the webinar, you may ask questions using the webinar tool. You can type in questions, but unfortunately, I will not be able to answer these questions immediately. I will do my best and answer them in the afternoon by email. That's one thing. The other thing is you will get the presentations which I showed today and access to a webinar recording later by mail. Okay, now we really start. Again, welcome to the webinar about unit testing and code coverage measurement with Tessy. I would like to give you a quick overview about the outline of the webinar. First, we have to delve a little bit into unit testing theory. Then under point 2, I will show you the tool in practice so you can see how it works. And concluding, I will give you a quick overview of all the features, the main features that we did not touch during the live presentation, so you get an idea what else you could do with Tessy. Okay, the unit testing theory, it's a different presentation, and it is also divided in 2 parts. In the first part, we talk about unit testing of C or C++ programs in general. And in the second part, I need to explain how the internals of Tessy work, because most of the things are invisible during the practice demonstration, so it's good that you know what happens. The primary question when we talk about unit testing of C or C++ programs is, what is a unit? And this is depending on the programming language. If we talk of C as a programming language, the functions are the units. So the functions in the sense of C are the units, and these units can also be called modules, because unit testing and module testing is more or less the same for me. And if the programming language is C++, analogous methods of the objects of the classes are units or modules, which means the test object for unit testing or module testing. Having clarified this, we can think of a software application as consisting of units. The rectangles, here the red rectangles represent the units, and the red arrows represent the calling hierarchy. And if we have the question, what does unit testing mean for such a unit here, I pick a unit which has a calling unit above and calls itself another unit. So the question is, what does unit testing mean for this unit here in the middle of this blue frame? And this is shown on the next page. Unit testing means that the unit under test is tested isolated from the rest of the application, and it is tested rigorously. This means that you especially try to input maybe unexpected values for the unit and see what happens. The isolation is at 2 points. It's isolation to the calling unit, which is depicted here at the top of this picture, and the isolation is also to called function in case your unit under test calls other functions. The isolation to the calling function has a big advantage. It allows you to call the unit under test with arbitrary input data. Have a look at this situation here. We have here the function f2, which is called from f1, but only if the parameter which is passed is not null. This means if you test f1 and f2 together, you will not be able to find out if the null pointer is recognized correctly and if the correct value is returned by the statement which is displayed in red. So this is not possible during integration testing or system testing. But if you perform unit testing of F2, it's technically quite simple to pass a null pointer to F2, and this allows you to see if the null pointer is detected correctly and also if the correct value is returned. And this also allows you to have 100% code coverage for F2. So code coverage should be measured during unit testing. That's another point here. This is the advantage of the isolation to the calling function. I said there's also isolation to the called function. In case you do pure unit testing and your unit under test calls another function, this function which is called is replaced by so-called stub functions. And this means that everything outside the blue line, which I usually call the interface of the unit, is under your control. This is the test environment, the test driver, and it cannot change without you know it or notice it. So it means this is a prerequisite for deterministic testing. Unit tests usually are deterministic, so it means if a test has a certain result, this will not change, and you will get the same result if you repeat the test in a fortnight. This means this isolation is a prerequisite for regression testing, which means reproducing your tests and your test results, maybe after you have refactored your test object. As I said, the blue line here, I usually call this blue line the interface. And on the next page, we have a closer look on this interface, and we see an additional advantage of the isolation to the called function. This here depicts the interface of the unit under test of our test object. It is divided in two parts. The upper parts, I think it's quite clear that the interface consists of the input variables, which means the variables that are read by the test object, and it consists of the output variables, which means the variables that are written by the test object. Of course, a variable can be input and output. Consider global variable which is incremented by the test object, and this variable value is first read by the test object, then it is incremented, and then it is written back, so it is input and output. If the test object has a return value, the return value obviously belongs to the output variables. This was the upper part of the interface, which might be quite clear for you, but please keep in mind that we have also a lower part in case our test object calls other functions. Then the parameter values which are passed from the test object to the called function are results, output variables of our test object, and for instance the return value which is returned from the called function to our test object is an input to our test object. So this allows you, for instance, to return arbitrary values in a test object if you use a stub function instead of the actual implementation of the called function, because the actual implementation cannot or will not, hopefully not, return illegal values, but a stub function easily can, and this allows you to check if your test object behaves correctly if unexpected value is returned. Okay, on this page here we see the situation after the process step unit testing. This means all the rectangles are green, which means the unit has passed their tests, but the arrows are still red. At the end of unit testing, we do not know if the units integrate correctly, cooperate correctly. This is left to the process step of integration testing, which you can do with Tessy, but which is not subject of the current webinar. This was about unit testing in general. Now a closer look on how unit testing with Tessy works. We already know what the test objects are, and testing with Tessy starts by specifying a source module to Tessy, and Tessy analyzes this source module and lists all the possible test objects, which can be functions in the sense of C or methods of C++ class. But the important thing is that Tessy determines the interface of each test object. And you know already what the interface is. We have here a simplified version of it without called functions. And the table at the bottom displays a very simple interface. The first two lines in this table, which are shaded in gray, describe a very simple interface, an example interface. It says, for instance, our interface consists of a variable A, which is input, of a variable B, which is input and output, of a variable C, which is only output, and our test object should have a return value, and this is, of course, output. And the interface determines the structure of a test case. Therefore, we can create a test case by assigning values to the variables of the interface. For the input variables, we assign values prior to the test, and for the output variables, we assign expected values after the test. So the third line here, the line shaded in yellow, depicts a test case. It says, okay, prior to the test, A should have the value 5. Prior to the test, B should have the value 4, and we expect that after the test, the value is 8. C is output only, so therefore we only need a value after the test, which is 17 here in this example, and the return value of the test object for this test case should be 42. So the interface determines the structure of a test case. And creating test cases, which means deciding how many test cases we need and which values they shall use, is a human task, in my opinion. And so there's no automatism, and we will see how it is done in Tessy. There are several ways. And after you have defined the test cases, everything else is automated. The first step is that Tessy creates what we call a test application. The test application is depicted here. The heart of the test application is a test object. And you see that it's a standalone application. It has its own main, and the blue parts here are generated automatically by Tessy. So even if you direct Tessy to create stubs, so the stub function code is created automatically. And if you want to run this test application on a microcontroller, certain microcontroller, and you need certain startup code, so the startup code is also added to this test application. The test data is not included in the test application. This means the test application does not increase with increasing size of test cases. The test application always has the same size, regardless if it is for one test case or for 100 test cases or whatever. The test application is created as C source code. So the next step is to compile this test application in something executable. There are mainly two possibilities for the compiler which you can use. On the left-hand side, you see the situation where we use a native GNU GCC or G++ compiler, and as this compiles the test application to a Windows executable, and you can execute the tests on the PC without hardware for the microcontroller or whatever. The second possibility is depicted on the right hand side here. You can direct Tessy to use a cross compiler that you use for your embedded project. For instance, a Kai compiler, tasking compiler, or whatever. This compiles the test application in a binary for a certain microcontroller, and then you need an execution environment which is able to execute a binary for that microcontroller. And usually, the debugger software which you use in your development environment is this execution environment. And this execution environment can act as an instruction set simulator, or it can be the interface to, let's say, a JTAG debugger, BDM debugger, or a circuit emulator, or something like that. This is not important for Tessy. Which compiler you use, yeah, influences the relevance of the test. If you use a GCC compiler, yeah, the test relevance is rather low, so you have maybe different integer sizes with respect to your target microcontroller, or different endianness and so on. So it's easy to use, but usually you cannot really rely on the results. The relevance of the test is much better if you use a cross compiler, which you use for embedded project. You can use it in the same version, in the same optimization level, and so on. And so the test application is rather near to what you later will have in your system. And yeah, there's also a difference if you use the instruction set simulator or if you execute the tests on the actual hardware, but this difference is not so big as it is shown here. Therefore, the arrow here has a gap. So the difference in the relevance of the test between instruction set simulator and actual target hardware is rather small, in my opinion. Let's have a look on these two situations here, where you execute on the host only and on the actual microcontroller on the left hand side. You see that the debugger acts as instruction set simulator and no hardware is involved. On the right hand side, you see that the debugger acts as interface to a hardware debug system, a BDM debugger, JTAG debugger, or something like that, and the tests are executed on the actual target hardware. And you see that Tessy communicates with a debugger in both cases, so Tessy does not really know where the tests are executed. It's the same for Tessy. The only difference is if you want to run the test application on the actual target hardware, yeah, the memory layout of the actual target hardware has to be considered, so that you have RAM where you think you should have RAM, and so on. So the steps up to now are: Tessy creates a test application, Tessy compiles a test application, Tessy loads the test application in the execution environment, and then the tests are executed in 4 steps. In the first step, the test input data is transferred to the text execution environment. In step 2, the test is actually executed. In step 3, the results of the test are fetched back from the execution environment, which could be the RAM of your test hardware. And in step 4, Tessy compares if the expected result is the same as the actual result, and if yes, the test has passed, and if no, Tessy has 2 features which you can use to debug your test case. The first thing is quite simple. Tessy can execute single test case. You do not need to execute all the test cases that you have in a row. You can pick out a single test case. And the second thing is more important. Tessy can place a breakpoint at the beginning of the test object. This would mean if you execute a single test case with this feature enabled, define breakpoint enabled, you stop the test execution in the debugger in your test execution environment, and then you can do line steps and see why a test object, why a test case did not return the expected result. Yeah, this is what I want to show you now in a practical demonstration. This here is Tessy, the user interface of Tessy. Those of you who are familiar with Eclipse will see that it looks like Eclipse. This stems from the fact that Tessy is based on the Eclipse-rich client platform. So we have the perspectives here. For instance, here we have the overview perspective where we will work a lot, but we have also perspectives we will not use here. For instance, the requirement management perspective for defining requirements and linking them to test cases. This is an interface perspective where we'll see the interfaces of the test object. We will see this later. This here is the classification tree editor perspective, which allows us to draw classification trees and create test specifications according to the classification tree method. This will not be covered in the seminar webinar at hand. The test data editor is where you create test cases and execute tests. We will make use of it. The scenario editor perspective is used for integration testing, which is not the topic of this webinar. And in the script editor, you can see a textual representation of the test cases. Maybe we have a quick look at it. In the coverage viewer perspective, you see the code coverage results and information, and the IDR. I explain if I will use it. Probably not during this webinar. Okay, all the perspectives have views which are considered useful for a certain task. In the overview perspective, we have the test project view, and in the test project view, the test cases are organized. Usually, if you start a Tessy without tests, this view will be empty, and you can create a tree-like structure to organize your tests. The root of the tree is called a test collection, and we can give it a name. And below this root node, there's an arbitrary structure of folders. You can also give the folders a name, for instance, F1, and this structure here corresponds to the layout of your source code directories, because the roots of this, the leaves of this tree are usually connected to modules of your code. You can give it also a name, for instance. So, and as I said, these modules are connected and linked to source files, C source files or C++ source files. But prior to proceeding, I would like to ask you a question about the programming language of the example. You can decide about the programming language which I shall use. I offer you C or C++, and it's now up to you to vote. The vote is still ongoing. Okay, now it does not really change anymore, so I can close the poll, and I would like to share the results with you. And the result is quite clear. 94% vote for C, so the decision is clear. I will use C source code for the test object, and I would like to ask another question. What shall be the development environment which I shall use for the example? You can select between the GCC compiler and having ZTT as debugger, or you can select the Kyle compiler for a Cortex microcontroller, where we would have microvision as the execution environment. And the third possibility is using an IAR compiler for MSP 430. using the CSpy debugger, which is included in the embedded workbench from IAR. Tessy supports a lot more cross compilers. You can find a list on our website. Yeah, I think the poll is now has found a result, so I'll close the poll, and I also want to share the results with you. And I think here also the result is quite clear. The GCC has 65%, and so I will now use a C source file and GCC as debugger, and GCC is already selected as compiler, and there's a possibility to select different compilers, but GCC is already the right setting here. The next thing which I need to do is I need to browse for a source file, and I take this one here, a C source file, which is called isValueInRange, and I would like to show you what's the contents of this C source file. It contains only one function, which will be our test object. The function is called isValueInRange, and it's, as I said, the only function here, and it's so the function solves a very simple problem. It shall decide is a value inside a range, and the range is given by a start value and a length, and the range is given by the structure, and the return value is yes or no, which means it's inside the range or not. And if you use the values 5 for the start and 2 for the length, and we want to know if 6 is inside or not, so 6 is inside, 5 is inside, 4 is not inside, and 7 is also not inside as according to the specification. But due to a programming error in this test object, if we use the values 5, 2, and 7, we will get the result yes, which is wrong. We need a no, and this allows me to construct a test case that will fail. Okay, usually you should know what your test object should do and how it looks like. The next step here is what I do now. I let Tessy analyze the C-source module, which means Tessy will find out how many possible test objects are in it, which is only one in our case. And Tessy will also determine the interface of this function. The first time takes a little bit longer than usual, but now we have the result. We have here one function, isValueInRange, and if we switch to the interface editor perspective, we see the interface of this function. We have a very simple test object. We have no external functions, no local functions, no external variables, and no global variables. We only have two parameters. The first parameter consists of a structure with two components. The first component is a start value, and the second component is the length of the range. And the important thing is that Tessy has determined that both components have the passing direction in, which means they are only read by the test object. So only read means not written. And Tessy had determined that they are not written. That's one thing. And this also is relevant for the test cases because we need to specify values for the start and the length prior to the test. And I think that's clear. If you want to find out if a value is inside a range, you need to specify the range. And also the value here as a variable v1 is the second parameter of our test object. It also has a passing direction in. That also means it is only read and not written by the test object. And this also means we need to specify a value prior to the test. The passing direction out is here only for the return value of the test object. I think it's clear, I said several times, if you have a return value, it's always output. So this is our interface, and please remember the interface determines the structure of a test case. Test cases are specified in the test data editor perspective. If I switch to this perspective, I can create a new test case in the lower left view by using the context menu new test case. And if I do so, I will get a column for the test data in this upper right view for the test data. So if I click on new test case, I get a column here in this view, and the yellow shaded input fields show me where I need to enter input data. The column is organized that the inputs are at the top and the output values are at the bottom. So I can now insert data here. I say, for instance, I would like to be the start of the range 5 and the length should be 2, and I want to know if 6 is inside or not. And according to the specification, yes, 6 should be inside, so therefore yes is the correct expected result for this test case. And I save this test case here, and I be able to copy this test case and paste it, and this gives me a second column, a duplicate of the first column. I can change it. I want to change the 6 to a 7, and the specification says 7 is not inside the range, therefore the expected result is no, but you know that this test case will fail. The next thing is I execute both test cases without instrumentation. I will explain this later. And now Tessy creates the test application, compiles it with a GCC compiler, creates a Windows application, executes the both test cases with the Windows application, and we should then see the results if the test cases has passed or failed. We now have the result as expected. The second test case has failed. The actual result is yes, but we have expected no. And at this point, I would like to create a test report just to see how easy it is. Just a click of the mouse generates a test report. Several formats are available: PDF format, HTML format, Word format, and XML format, which is always generated. I have selected HTML, which starts my my browser, and you can now see the test case. Important is the second test case has failed. The input values were 5, 2, and 7. The actual value was yes, we expected no, it was not equal, and therefore the test failed. This is a very simple test report. For instance, the test cases have no names at the moment, no specification, and such things, but just to give you an impression. The main problem is now to find out why the second test case has failed. And as I told you, we have the possibility to execute only the second test case and have the feature defined breakpoint. And if I do execute with this feature, the test will not run until its end, but we will end up in the debugger, in the software debugger, which in our case is the CDT debugger. You see now here we are at the beginning of our test object, and we can use the debugger to see the values of the input data, and we see we have 5, 2, and 7, which means we are in the second test case, and we can now do line steps. And yeah, I would expect that the return no in line 43 is executed. So this would give me my expected return no, but if I do another line step, I see, okay, it is not executed, and the cause of it is a missing equal sign in line 42 in the decision of the if. And as soon as you know what could be the culprit, you can execute the test to its end, and we can use the built-in editor of Tessy, the CDT debugger, to fix the bug. I use edit source as before, and I insert an equal sign here, which will remedy our problem, and I save it, and I go to the test data editor perspective, and I run this test case again, but now without the check mark here. This and this will allow me to see if our bug fix has worked. And okay, so we have now a green result. That means our bug fix has remedied the problem. I have intentionally executed only the second test case because to show we do not really know if the first test case still will pass or not, because we have changed the source code of the test object and we have no current result for the first test case. But it is easy to obtain such a result by just clicking on this execute test button, because this here will execute all the available test cases, and this will allow us to see if the first test case was spoiled by the change in the source code. And we are lucky, the first test case still passes, but we need to verify this, so and we have done it now. Okay, now we could say we have managed everything. We have two test cases pass, but an important question is still open. Which coverage have we reached by these two test cases? And it is quite easy to determine this. I just direct Tessy to execute the two test cases again, and by selecting an instrumentation, Tessy measures code coverage. In this case, branch coverage and modified condition decision coverage, but you see that you can select other measures also. And now I re-execute the test cases, and instrumentation means Tessy now inserts counters in the source code to find out which test case executed which branch and which condition of a decision was exercised by which test case. So the source code now looks quite different to what we have seen before. And it's important to note that if you develop or test for safety critical application, that you do the code coverage measurement in a separate step like I did it here. So first execute without instrumentation the test cases to find out if they are functionally correct, and then execute with instrumentation to find out which coverage we have reached. And now the coverage result is present. We see we have only reached 75% of branch coverage, and the same for MCDC coverage. So we have to have a look in the coverage viewer to find out what has happened and what was executed and what not. In the coverage viewer perspective, you see a flowchart of your test object, and we see also the source code of the test object here in the lower part, and the lines shaded in red are not executed, and the lines shaded in green are executed. Same as with the branches here. We have here in the flowchart a red branch, and this means this branch was not executed. If I click on this branch, I see that the return no of the first if instruction is highlighted. So we need to execute, or we have not executed the send part of the first if. The flowchart shows both test cases together. If we, for instance, only mark the second test case, we see the path of the second test case through our test object, and we can also click on this branch here, the green branch here, and we see, okay, so this branch here corresponds to the send branch of the second if instruction, and so this means the second test case has executed the send branch of the second if instruction. And if you remember, that was the reason why we introduced an equal sign here. So everything is correct, or we can also click on this red diamond here, and this shows us the MCDC coverage. So we see we have only 50% because we did not execute this decision with an outcome of true. Okay, that was what I wanted to show you on Tessy, and our last concluding step would be to have a very, very quick overview of the main features that Tessy has in addition to what we have seen. And yeah, first of all, Tessy has a certificate from the TÜV Süd in Munich, which states that Tessy can be used for testing of safety critical application according to, for instance, 61508, 26222, 26262, which is the automotive standard, 50128, which is railway standard, or 62304, which is a medical standard. And it can also be used for other standards because certificate covered 61508, which is the mother standard. It's also a tool qualification package available for Tessy. So in case you need to qualify your testing tools, you can do this by use of the tool qualification package. As I said, Tessy covers the process step module testing or unit testing. There are two names for this process step, and Tessy also covers the process step integration testing. So integration testing, you can consider integration testing as having several units together forming a bigger test object, which is called component in the terminology of Tessy. And inside that, the components are the units and data, and they communicate in some way, and they are stimulating inputs from the outside, and you can also call other components. So that's roughly the integration testing feature of Tessy in an abstract way. So we have a component is a test object of integration testing. Where do you need it? For instance, for a stack, where you have push and pop operations, which you need to test integrated. Another thing that Tessy can provide is requirements management. So it's possible to create requirements in Tessy or to import requirements from the outside from your preferred requirement management tool. Tessy supports the requirement interchange format file standard, which most requirement management tools can create. And so you can create requirements or import requirements, can link them to test cases, and then you see if all the requirements have test cases and if these test cases have been executed and passed or failed. So you get reports about the requirements coverage. Another feature of Tessy is that you are able to generate test specification according to the classification tree method. This is a systematic method. It's a visual method. You see here what we call the classification tree, and the classification tree has equivalence classes. You see here for steering angle, we have 3 equivalence classes, left, central, and right. And if you know about the tables in 26.26.2, you see that you have to have equivalence classes in your test case specifications, and also boundary values and such things, which can be created or visualized by the classification tree method. As with requirement management, you can also use Tessy without requirement management, without classification tree method. It's included in the license, but and you are free to use it, but you don't have to use it if you prefer, for instance, to create your test cases in an Excel sheet, which is also possible. Tessy can display test data graphically. We see here in the middle the test input data of 20 test cases. The beige step curve is the input data, and the actual values are the green ones, and the expected values are the blue ones. And you see that most of the time actual and expected have the same value, but for 3 test cases there's a slight difference, and this is shown graphically, and you can understand it much more easily than if you have a lot of data. I said Tessy has a script editor which allows a textual representation of test cases. You see here an example. The main intention for this is that you can save the test cases in this format, which is an ASCII format or text format, and this allows you to compare the current state of the test cases to a state, let's say, a week before. Tessy has a command language, so this means you can operate Tessy from the command line without user interface, which means in headless mode, which also allows to write batch scripts, command scripts, which you can execute automated. That's useful if you want to integrate Tessy in continuous integration systems, for instance in Jenkins, or if you just want to do your regression testing in an automated way. Tessy also measures some metrics, so Tessy has also a little bit of static analysis. The most important measure is the cyclomatic complexity, and you can have thresholds for warning or error, and we see here, for instance, screen 2 is below the warning threshold, so it's displayed in green. 12 is higher than the warning threshold, but below the error threshold, and 22 is above the error threshold. So that's all I wanted to tell you. I hope you have enjoyed it and it was useful for you.